So before I get started, I just wanted a funny backstory behind why I ended up choosing this topic. Because originally I'd been thinking about some other topics that I wanted to do a talk on. And I actually got into a disagreement with my cousin-in-law, who is an engineer. We were talking about patience with children, you know. And he said, oh, you have 1 divided by 0 patience. Your patience with them is unlimited. And I said, no, actually, my patience with them is undefined. I don't have any patience with them right now. And so we went back and forth, and he was like, no, because your patience is 1 over 0. You're approaching infinity. And I said, nope. Really not. And so I finally said, can you just admit that you're wrong about this, that 1 divided by 0 is not infinity? And he said, no, that would never happen. So what I'm actually going to do is send him this PowerPoint after I give this talk, and then hopefully he'll say, Andrea, you were right. I'm wrong. We'll see. I don't know. Probably not. I'll let you guys know. Okay, I'm going to see if this clicker is actually going to work. Okay, so I'm going to talk about ultimately the problem with dividing by 0, but, oh, it works. Okay, a couple of things. So first of all, we're going to talk about just some interesting things about 0. So in ancient times, when we started counting and things like that, 0 did not actually exist for quite a while. Because people just needed math to count things and to keep track of time. So if you don't have any sheep, then you don't need a number to express that because you're not counting your sheep because there are no sheep to count, okay? So there were at the time that 0 finally surfaced, started coming around, there were a lot of different number systems going around. Romans had a number system, the Greeks had a number system, Babylonians had a number system, and everyone was kind of different based on different bases. For instance, Babylonians, which we're going to talk about in a second, was actually base 60. Okay, so this is the system that actually gave birth to 0, but just as a placeholder. So they didn't actually assign any value to it quite at this time. They just used it as a placeholder. Because in this system, the symbol for 1, 60, and 3600 were the same. And so things got more complicated when you were talking about 61, 3,601, or 216,001. Okay, they couldn't tell the difference. Well, if I write this, which one am I talking about? So they decided to come up with a symbol for a placeholder, which would ultimately then become 0, where they could separate. So now we could say, okay, if we have 2 of them, this is 61. If we have this placeholder now in the middle, now we know it's 3,601. And then if we have 2 placeholders, we know that it's 216,001. So they added in this placeholder, but they didn't assign it a value. So they never used the symbol on its own by itself. It was just a digit that they used so they could tell the difference between the other numbers that they were actually using. And so this went on for almost 2 millennia. The Greeks, the Romans, they wanted nothing to do with this placeholder, this kind of beginning idea of 0. So for almost 2,000 years, the Babylonians were the only people who really used this. Why? Because once you added in 0, it kind of started breaking all of the rules that we had in math. So the normal rules that applied were now broken when we added in this idea of 0 or nothing. So just thinking about the number line in general, when we're adding, so if we're at 1 and we add 1, well, now we're at 2, so we're getting larger. If we're at 2 and we add 2 to that, we're at 4, we're getting larger. But when we add 0 to 0, we don't go anywhere on the number line. We just stay where we're at. So this violated the axiom of Archimedes, which said, if you add something to itself enough times, it's eventually going to exceed everything else in magnitude or in size.
Am I allowed to ask a question?
Yeah.
So in a number line, before there was 0, what was between -1 and 1?
Nothing. And actually, when they started putting 0 on the number line, they had it in all different places. So they couldn't figure out in the beginning where to put this value of 0. So anyway, this idea actually started with the difference of 2 unequal areas. But so adding 0 kind of broke this rule. It's not getting any bigger. It's actually just staying the same. But everything else that we add together is getting larger, and 0 is defying that. So that's a problem. Now with multiplication, again, we have this issue where other numbers are doing things that 0 doesn't seem to do. So for instance, when we multiply by 2, we're essentially stretching the number line out. We're making it larger. We're making the space between 0 and 1 bigger. So in between 0 and 1 now, that space up here is twice as big. So multiplying by 2, this number line is getting bigger. If we multiply by 1/2, then we're kind of shrinking the number line. So the space between 0 and 1 now is getting smaller. So if we thought about 1 being right here, now it's half of the size. So if we multiply by a number larger than 1, we're kind of stretching that number line out. If you almost think about it like a rubber band, we're stretching that number line out. And if we're multiplying by 1/2, we're kind of shrinking everything together. Well, when you multiply by 0, everything just becomes 0. We've broken the number line. There's no number line anymore. So this is another problem. So 0 is ruining addition, and now it's ruining multiplication. So then, to make things even more complicated, now they get into, well, what happens when we try to divide by 0? So we're going to start with some basic math examples, work our way through some algebra examples, and then I'm going to talk about some limits. So just regular math here. We know that 15 divided by 5 is 3, because if we add 5 together 3 times, we get 15. Okay? But 15 divided by 0, what is that? Because we can never add enough zeros together to get to 15. It's an unlimited number of times. It's never going to get larger, like we talked about with addition. There's never enough zeros we can add together to get 15. Pizza. Okay, this is one, my oldest son is in 4th grade, and so they're working on division, and we've kind of talked about this. And this is, I use cookies with them, but same idea with pizza. So we have one pizza. We're going to divide it by 2 people. So each person's going to get 50% or half of the pizza. So when we're dividing it by 2 people, each person gets a half. And then again, we have a pizza. Now we're going to divide it by 5 people. Every person's going to get a fifth, or 20%. So if everyone's going to get a fifth, we can feed 5 people using that pizza. Now we have one pizza, and we're going to divide it by 0 people. So everyone gets 0% of the pizza. So what is that? 1 divided by 0. Well, there's no number that satisfies that. We can actually feed an unlimited number of people because we're not feeding anybody, because nobody's getting any of the pizza that we have, okay? And everybody's sad. So there's no single number here that would answer 1 divided by 0. We don't have, like with 15 divided by 5 equals 3, we don't have a singular answer to go along with that. Okay, so another thing, and we talk about this a lot in some of our 097 classes, is thinking about checking division using multiplication. So we know that 12 divided by 4 is 3, because if we check it 3 times 4, we get the original answer back. The product is what we originally started with. And then 20 divided by 5 is 4, because 4 times 5 is 20. So working backwards using multiplication to check our division. So if we assume that 10 divided by 0 is 0, then that means 0 times 0 would give us 10. But we already know anything times 0 is equal to 0. So we can't define it this way using division, or using multiplication. And so we could substitute 10 in with any number here, and it's still not going to work. Okay, well, but what about 0 divided by 0? Okay, because then if we check that using multiplication, right, and we say it's 0, then 0 times 0 is 0. However, let's look at numbers that are really close to 0 first. So we're assuming we're not going to use exactly 0 in the numerator or the denominator. We're just going to look at things that are getting smaller and smaller and closer to 0, but they aren't actually equal to 0. Well, if we assume that the numerator and the denominator are both 0.1 or 1/10, and we divide those, we get 1. Same thing with 1,000th, and then same thing here. So every time we're getting closer and closer to 0, we're still getting 1. So that means 0 divided by 0 must be 1, because any time we divide something by itself, we always get 1, right? 3 divided by 3, 5 divided by 5. But what if we just leave the numerator as 0, because we're okay with that numerator being 0, but we're just going to look at denominators that are getting closer to 0. So we're going to leave our numerator as 0 every time. Well, 0 divided by 0.1, 0 divided by anything is 0. 0 divided by 100th is also 0. So every time we're getting closer to 0, we're still just getting 0 each time. Well, up here we were getting 1, and down here we're getting 0. So is it equal to 0 or is it 1? We don't know. So we can't define it because we don't have an agreement here. And down here you can see the same is true with negative numbers as well. Okay, so on to algebra. Why can't we have a rational number, so a number that can be written as a fraction with a denominator of 0? Why can't we do that? So we're making an assumption here that we've established a set of rational numbers using sets and operations that we've already defined. So we're using things that have already been defined. So we've defined rational numbers as a set of integers, and then addition and multiplication. We've defined those. So starting with an ordered pair, A, B, assuming that B does not equal 0, we have this binary relation where AB is equal to the ordered pair CD if and only if AD is equal to BC. So when we multiply, essentially we're using cross multiplication here, we get this equivalence relation. Okay, so these are some assumptions that we're making for this one. So if B does not equal to 0, then and A divided by B is equal to C. We can just get rid of this B in the denominator, multiply both sides by B, and we get A is equal to B times C. Okay. Now let's assume C is a number that we can figure out, and we know that A divided by 0 is equal to C. So that means we can use the same principle here where we're just going to multiply both sides by 0, and we get A is equal to 0 times C. But because 0 times C here is just equal to 0, there's no single number that will satisfy this equation. There's no value we can find for C, just like we kind of talked about earlier, that's going to make that equation true. It could be any number that we could plug in for C. So as of this point, we cannot assign a numerical value to A over 0. So to demonstrate further using something other than A, 6 divided by 0, let's say that that's some value x. Well, then multiplying both sides by 0, x times 0 is going to give us 6. Well, we know that's not true because anything times 0 is just 0. So there's no value I can plug in. There's no number I can multiply by 0 and end up getting 6. So again, well, what about 0 divided by 0? So we'll assume that 0 divided by 0 is equal to x. And this means we have to find some value for x here. So again, x times 0, multiplying by 0 to get rid of it in the denominator, x times 0 is 0. Again, there's no one number that we can substitute in for x. It just, any number in here would work. It could be -5, it could be 3, it could be infinity. We don't know what it is because every number is going to satisfy that. Okay, so using properties of multiplication and division, we know that if we take a number, we divide it by another number, and then we multiply by that same number, we're going to get our original number. So for instance, if we take 10 and we divide it by 2, and then we go back and we multiply it by 2, we're going to get right back to 10, because the division and the multiplication are essentially undoing each other there. We also know that any number times 0 is going to be 0. So any x times 0 is going to give us 0. So let's just assume that x does not equal 0. And we're going to assume that there's some value k that we can define where x divided by 0 is equal to k. But again, we're assuming that x is not 0 here. So following this same idea up here, and then multiplying both sides by 0. So we're just basically rewriting this division. Instead of using a fraction, we're just going to rewrite it using the division sign. And we're going to multiply both sides by 0. So I'm taking x, I'm dividing it by 0, and I'm multiplying it by 0. Well, from this principle up here, that says we should get right back to x, because I've taken a number, I've divided it by a different number, and then multiplied by the same number, so I should get right back to x. And then I'm going to take the k here and multiply that by 0, which we just said any number times 0 is 0. So this gives us, when we do that, this all becomes x, like we talked about, and then this becomes 0, so we're left with x equals 0. This is a problem because we started out assuming that x does not equal 0. So we've just contradicted what we were trying to do. We started with the assumption x does not equal 0, and then we ended up getting x equals 0. So that does not work. Okay, let's look at the function f of x equals 1 over x. So we're going to look at numbers that are really, really close to 0, but not equal to 0. So if we divide 1 by 0.1, we get 10, and so on. We get 100, 1,000. So each time we're dividing by a number closer and closer and closer to 0, our function, 1 over x, is getting larger and larger and larger. So it actually appears to be approaching infinity. So 1 divided by 0 must be equal to infinity. But if we look at negative numbers instead, so our values of x are now going to be closer to 0 but negative, so we're getting closer and closer and closer, but we're still negative. Now our numbers are getting larger, but they're getting more negative, so we're approaching negative infinity. So 1 over 0 must then be equal to negative infinity. But we just said, well, it must be equal to infinity. So again, we have this contradiction. Is it approaching infinity, or is it approaching negative infinity? We don't know what's actually happening right there at 0. So again, this is just a graph of this. So you can see that as our x values are getting smaller and smaller, we're approaching positive infinity here. And then as we're getting closer and closer to 0 on the negative side, we're down here approaching negative infinity. And so we can't figure out what exactly is happening right there at x equals 0. Okay, so if we allowed division by 0, if we said, yep, you can do that, and we defined it as either equal to 0 or something else, a couple of fallacies would occur. Some things would happen. Okay, so we're given that x times 1 equals 0, and as I said x, 0 times 1 equals 0, and 0 times 2 equals 0. Any number times 0 is 0. Then, because they're both equal to 0, we can set them equal to each other. So 0 times 1 is equal to 0 times 2. We're good so far. And now we're going to allow division by 0. We're going to say, OK, we're going to divide both sides of this equation by 0. So if we divide, we're going to divide 0 by 0 here and 0 over here. So then we're just left with 1 equals 2. So we got rid of the 0 on each side, but now we're left with 1 equals 2, which obviously we know is not true. So if we allow division by 0, that's one problem. Now we have, any number can then be equal to any other number. Okay, let's look at another one. Let's let 1 be equal to x. So I kind of wrote out the steps over here and then the math over here. Let's multiply both sides by x. So we get x times 1 equals x times x, which we can simplify to x equals x squared. And then we'll subtract 1 from both sides. So subtracting 1 here. And then we're going to divide both sides by x minus 1 to get rid of this side right here. And so remember, we can factor this into x plus 1, x minus 1, because it's difference of squares. So we're going to take each side here, and we're going to divide it by x minus 1. And that's going to give us 1 equals x plus 1. So if we go back where we assumed 1 is equal to x here, and we replace x with 1, we get 1 equals 1 plus 1, which means 1 equals 2 again. So again, we have this issue because we allowed division by 0 right here. We assumed x was 1. So this is 1 minus 1, which is 0. So when we allow that division by 0, we again end up with something that is not true. We end up with another fallacy. Okay, let's look at limits. Can we define a over 0 using limits? So let's consider the limit of a over b as b is approaching 0. So for any positive a values, that we're looking at the limit from the right. So this is similar to f of x equals 1 over x. The limit from the right, so as we're approaching 0 from the right of a over b, as b is approaching 0, is going to be positive infinity. We're getting closer and closer. We're approaching infinity. However, if we look at the limit from the left, so the limit as b approaches 0 from the left of a over b is negative infinity. So we have two one-sided limits that aren't the same, so we cannot define the two-sided limit because they don't agree with each other. So this is the same as the limit as x approaches 0 of 1 over x. So same thing. If we look at it from the right, then we're approaching positive infinity, and if we look at it from the left, we're approaching negative infinity. And so since they don't agree, they do not exist. Well, what about the limit as x approaches 0 of 1 over x squared? So this is where people got creative. Because when we're working with limits, if we're looking at that right now, we're saying, well, that's division by 0, and so we're not going to allow that. You can't have division by 0. So any limit, anything that's going to give us 0 in the denominator, we just can't define. Well, in this case, if we look at the graph here, as we're approaching it from the right, we're approaching positive infinity. And if we're approaching it from the left, we're also approaching positive infinity, because anytime we are squaring a number, it's going to end up being positive, whether it's positive or negative. So now the one-sided limits agree, so we can say that the limit of 1 over x squared as x approaches 0 is equal to positive infinity or just infinity, because those two limits agree. Again, the thing with limits, though, is that we're looking at what's happening as x is approaching 0, not what is happening right at 0, which I just said. Okay, but wait. We're told that the limit as x approaches 0 of sine of x over x is equal to 1. So how is that if we can't divide by 0? Because if we have 0 here, we can't do that. It should be undefined. So how can they say it equals 1? So we're going to look at how they came up with this. First of all, we're going to assume that x, our angle, is between 0 and pi over 2, so it's in the first quadrant here. BAC here, or actually just BC, is a sector of, we're going to look at this on the unit circle. So we know that we have a radius of 1 here. So BAC, and then this is the arc right here, BC. So from C on the unit circle down to what essentially would be the x-axis here, if we're thinking about this on a coordinate plane. This distance right here is our y value, which in trig is the sine of x. If we're looking at DB, the side of this larger triangle right here, and we're looking at our x value, we have DB is our opposite side over our adjacent side. So because we're on the unit circle, we know that that adjacent side is equal to 1. Okay? So opposite over adjacent is tangent here. And so that's going to be equal to dB. dB is going to be equal to the tangent of x. So looking at the areas, so we're going to start with this little triangle right here. So A, B, C. Area of a triangle is half the base times the height. So if we're looking at the base, that's just going to be 1. And then the height we just said was the sine of x. That's that perpendicular distance right there. So if we have 1/2 the base times height, and we simplify that, we get sine of x over 2. If we look at the sector of the circle, so basically it's this triangle here, but we have this little added piece here. That's equal to our angle over 2 pi, because the entire circle would be 2 pi, times pi times 1 squared. So area of the circle, pi r squared. We know that our radius is 1 because it's a unit circle. So simplifying this, 1 squared is 1. That gives us pi. These pi's cancel, and we get x over 2. So the area of just that kind of pizza slice right there is x over 2. Now if we look at this larger triangle, DAB or BAD, and we find the area of that, again, that's 1/2 the base times the height. So we have a base here of 1, and we said this height was tangent of x. So simplifying that, we get tangent of x over 2. So what we're going to do is we're going to compare these areas. So we have this small triangle right here. And we know that the area of this triangle has to be smaller than the area of this sector, because it's essentially this triangle plus this little extra piece right here. And we also know that this triangle has the largest area because it contains both the smaller triangle and the sector, so it has to have a larger area. So if we compare those, this ABC, we said was sine of x over x, has to be less than or equal to the sector, this little pi slice right here, which we said was x over 2. And then that has to be less than or equal to this large triangle, which we said was tangent of x over 2. So if we clear out the denominator here, we have the sine of x is less than or equal to x is less than or equal to tangent of x. And then to start simplifying this, we can think about tangent as sine over cosine. So taking that last one, hold on. Oh, it's going to make me, nope, just kidding. Okay, so taking this last one right here, picking up from there, we're going to divide by sine of x. So we get sine of x divided by sine x is 1. Then we get x over sine x, and we get 1 over cosine of x, because those signs from sine x over cosine x have canceled. So taking the reciprocal of this, we have 1 is greater than or equal to the sine of x over x, which is greater than or equal to the cosine of x. So using the squeeze theorem, the limit as x approaches 1, so the limit of this is greater than or equal to the limit of sine of x over x as x is approaching 0, is greater than or equal to the limit as x approaches 0 of cosine x. So now we're looking at the limits using the squeeze theorem. Well, the limit of 1 is just 1. And as x is at 0, the limit as x is approaching 0, cosine of 0 is 1. So we have 1 has to be greater than or equal to this limit of sine x over x, which has to be greater than or equal to 1. So we have 1 on both sides. It has to be greater than or equal to it, so it has to also be equal to 1, because there's no other value in between 1 and 1 where sine of x over x can fit. Okay, one more. Let's look at the limit as x approaches 0 of x squared times sine of 1 over x. So again, we have this problem where we have essentially 0 in the denominator. We can't just use the limit law because the sine of 1 over x does not exist as the limit approaches 0. But by definition of the sine function, we know that the sine of the function lies between -1 and 1. Okay? So sine of 1 over x has to be somewhere between -1 and 1. So multiplying everything by x squared, so we can get this x squared into the equation, we have negative x squared is less than or equal to x squared times the sine of 1 over x, which is less than or equal to x squared. And so again, using the squeeze theorem, we can look at this using limits. The limit as x approaches 0 of negative x squared is 0. And the limit of x squared as x approaches 0 is also 0. We can simply plug in 0 here. Then that means, because it lies in between the two here, that the limit of x squared times sine of 1 over x must also be approaching 0. So we have 0 is less than or equal to this function is less than or equal to 0. So by the same idea, it also has to be equal to 0. Okay, last thing, I talked way too fast. What is 0 to the 0 power? Okay, because normally when we look at how you get a 0 power and what that actually means, we use division to do that, and we use subtraction of the exponents. Let me see if I can find a working marker. So just as a refresher, if we're looking at x to the third over x to the third, we use subtraction of exponents to say this is x to the 0 power. Well, what does that mean? It means in the numerator we have x times x times x, and in the denominator we have x times x times x. So because this is multiplication, we can cancel these out. So x divided by x here is going to give us 1. X divided by x here is going to give us 1. And x divided by x here is also going to give us 1. So that all 1 times 1 times 1 is equal to 1. So because these are the same thing, just written differently, we know that x to the 0 power is 1. And that's true for any number to the 0 power. So exponents represent repeated multiplication. So 2 to the third, our base of 2, means we have 3 of those that we're multiplying together to get 8. Well, 0 to the 0 power equals, we don't know, because 0 times anything is 0. So it has to be 0. But, like we just said, anything raised to the 0 power is going to be equal to 1. So 12 to the 0 is equal to 1, so 0 to the 0 must also be 1. But because it's repeated multiplication, and we're multiplying by 0, then it has to be equal to 0. So again, is it 0 or is it 1? We can't define it. Also, if we just think about we're multiplying 0 times itself 0 times, that means we don't have anything there. We don't even have 1 0, because that would be 0 to the first power. This is saying we have 0 zeros, so what does that mean? Okay. The end. Questions? Comments? Cookies? Steve?
Way back when Tom asked his question, one popped into my mind too, and that is
Oop.
where 0 was, you had 0 on the number line between positive and negative integers.
Mm-hmm.
And his question had something to do with negatives, and then I got thinking, were people even thinking about negative numbers before 0?
No, because they're still thinking about counting and telling time, and so you're not thinking about negative sheep or negative ears of corn at that point in time, or negative time, in fact.
Okay.
So, but when they did finally accept 0 and all its faults, they really at first weren't sure where to put it, and looking at different number systems, they had it in different places on their number lines because they weren't quite sure what to do with it, because they started using it as a placeholder, and so we don't need to put it on the number line if it's just a placeholder. And then it represents nothing, and so where exactly does nothing go? When you count, you don't start with 0. You start with 1, so they weren't quite sure where do we put it. Other questions? Yes, sir.
In that same line of thinking, 0 is a placeholder
Mm-hmm.
versus 0 is a number. I can remember when I first began, learning about operations with numbers, being told, classmates told, 0 is a placeholder, and that was fine because there are no 10s, so you put 0 in the 10s place. As much as I understood this as a little kid, I don't really know how much I grasped the fact that 0 was also a number. I guess the question is, do you have any sense of when that transition began to take place? 0 as a placeholder versus 0 was actually a number?
Yeah, so it was like I was saying, about 2,000 years after they started using it as a placeholder, when people in the West were like, okay, we have to kind of accept this idea. And so then they started saying, well, if we're going to use 0 at that point in time, and it's a placeholder, then what is this digit doing with all of our other operations when we're multiplying, when we're adding? And that's kind of when all the wheels fell off the wagon.
So 2,000 years after what?
The Babylonians introduced it as a placeholder in 300 BC.
Because it is, you made it very clear that 0 is strange, does things that nobody was very happy with. I recall reading the story from a couple of math educators having a discussion in the 50s. One was very prominent, and the other was soon to be prominent, but at that time was a student. And the prominent math educator asserted that 0 is a placeholder and not a number. This is actually printed somewhere. The student asked something to the effect of, well, is 3 a number? Yes, 3 is a number. If you take 3 minus 3, what do you get when you get 0? If you take a number and you subtract a number, you still get a number. The prominent educator thought about that for a minute and said, I'll have to think about that.
Yeah, that's
There is still, I don't say confusion, but the role of 0 is sometimes not clear.
Oh, right. No, I agree. I mean, a lot of my students, if they solve an equation and they get x equals 0, then they're just perplexed. Yeah, they say it's no solution, or it's infinitely. Yeah, no, they'll just say no solution. And it's like, well, 0 is a perfectly good number. And they're like, but wait.
Well, it's interesting because then when you make a measurement, like in science, those zeros play 2 different roles. If you
Right.
For significant digits. So if you write 100 and don't put the decimal there, then you'd say, oh, those zeros are placeholders. But if you put the decimal there, you say, but I measured that and there was nothing there in the tens place or the ones place.
Yeah.
And so it plays that sort of dual role of, is it holding the place just so I know there's 100?
Right.
Or is it that's exactly, precisely 100, known to the ones place?
Right, exactly. And and it's even just thinking about normal everyday things like with pizza. I have 0 pizzas, or I have no pizza. So is it a number? Do I have a number of pizzas here? Or is it just a word I use to say that I don't have any? Any other questions, comments? Yeah.
You stated on your last slide that 0 times anything is 0. Is 0 times infinity still 0?
Yes.
Wouldn't that imply that 0 divided by 0 is infinity?
Why do you think you get yourself in trouble?
No. I did that just for John.
I won't forget it either.
Just for you. He's got something to say about this.
No, I think Jeff's question might infinity a number?
Right.
Because, and I'm sorry, I don't remember exactly what the slide says, but if the slide said 0 times any number,
Right.
0.
Right. And what I always tell my students about infinity, even working like in interval notation, where if it can be equal to something, less than or equal or greater than or equal to, in interval notation you're using that bracket. But we can't ever plot infinity on a number line. We can't plot that. So we can't ever say that something's going to be, we can't ever use that bracket next to infinity in interval notation because it's not something that we could actually plot on our number line.
Buzz Lightyear can.
Yeah, that's true. This is true, yeah.
In astronomy, singularities are defined as taking up exactly 0 space, which would give them infinite density. How do you reconcile that with your position of 1 divided by 0 not being infinity?
I'd have to think about that one. That's, I don't know.
Can anything in the physical world be of infinite extent?
I don't think so.
Well, then the density is not infinite.
The volume can't be 0. I think it's a-
But only 0 to as many place values as we can measure.
Yeah, it's always.
Yeah. That's true.
Right?
It's always,
So-
oh yeah, it's always the measurement.
So we can't measure to an infinite number of distant places, therefore,
It could be there and just unknown.
Anything
I
else?
don't think there are any measurements that go to singularities because you can't exactly measure.
so why do you call it 0?
I have
Because
actually looked at the
it
mathematics
gets so
myself.
close to 0 that we just say we might as well treat it as 0.
And you make assumptions like that all the time. Ideal gas law, you treat the volume of a gas molecule or atom molecule being 0, but it's to make an assumption to make your calculation easier because we don't have to do all the math involved to do the reality.
See, this is the issue mathematicians have with people who live in the real world. Things like physics and chemistry and astronomy, because it's a shame that Dr. Johnson's not here. I was actually going to go over and personally invite him, but I forgot. I don't know if he'd come anyway, but Johnson and I have been going back and forth for all 30 years about, is 3 over 0 undefined or is it infinity? And he maintains it's infinity and he's not budging. That's because he's a physicist.
Right.
They just want to use that because it's convenient. It's a convenient way of saying if you got something really, really tiny and you divide it into something that's not really, really tiny, it's going to be really, really big and we'll just call it infinity. That's nonsense, by the way, if you're in a math class. If it works for the physics people, we'll just turn a blind eye towards it.
Yeah. Mike.
Isn't it? I mean, it also seems to be part of the quandary is that we're treating different concepts with the same label, right? We've got a placeholder, we've got a number,
Right.
and I think to a certain extent we have a state. And we're talking about a state.
Yeah.
The absence of no.
Exactly.
Essentially, but and I just wonder if there's never been an attempt to disentangle this by labeling those different things in a different way. And your presentation is all about how interwoven that is and how challenging it would be. But
Right.
the ways that you might start to address that would be by calling these different things by different labels.
Right.
Isn't that kind of the idea of nothing and 0?
Yeah.
Which this whole thing was put together to resolve that concept.
Yeah.
Yeah. Yeah. And I was reading something somewhere where it's like, well, are they ever going to define 1 divide or something divided by 0? And it was like, no, look, we've been trying to do this for a long time and we clearly have not figured it out yet. So it was just, right. Everybody can have cookies. Unless there's 0 cookies and then you don't get any, which means all of you can have some because there aren't any left. Everybody can get 0 cookies on the way out. All right, that's all. That's all I got. Thanks.